Hello, we are going to explain today the flow in open channels. Well, the definition of an open channel is a duct in which the liquid flows with a free surface. In all of these pictures, you can see the water level doesn't fill up the pipe, or you see you can have open or closed channels, but always you have a free surface. That means you have the interface between water and air. That's the main feature of an open channel. We have two types of open channel flow. The first one is a natural channel. This is a good example of this is a river. Of course, rivers have an irregular shape. They are made by nature. And the second type of open channel is an artificial channel, like a canal or a sewer. Sewer is where the pipes that collect the wastewater, the brown water coming from your toilets and shower and kitchen. So these artificial channels, of course, they have a regular shape because they are man-built. This is an example of a natural channel, River Ebro. This is an example of a canal, artificial channel, Canal Imperial de Aragón, built in the 1900s. So the channel geometry, we have the following variables. We have y, which is the depth of the flow. That's the vertical dimension of the channel. Then we have A, the flow area. That's the cross section of the channel. That's the section of the picture below. P is the wetted perimeter. This is we have to add up all the sides except the free surface. That means the free surface is not wetting the walls. That's why we call it wetted perimeter. And finally, RH is the hydraulic radius. That's something equivalent to a pipe radius. So RH is defined as the area over the perimeter. We are showing in this slide some examples of common open channel shapes. For example, the rectangular open channel, we can see that the flow area is B times Y, and the wetted perimeter is P is B plus 2Y. We take away one of the B's because the top B is not wetting the walls. That's how we calculate wetted perimeter. And of course, the hydraulic radius is the ratio between the area and the perimeter, so we get by over b plus 2y. Similarly, we can have a wide flat channel. In this case, the horizontal dimension b is much larger, much greater than the vertical dimension y. So in the wetted perimeter, we can neglect the 2 plus 2y term that we had in the previous rectangular channel. Then the last example is a circular channel that has the formula shown below. Of course, we can have other kinds of channels like this trapezoidal channel, which is very much like the Canal Imperial de Aragón, and triangular channel like the one shown below. Here we are going to show you a video of ripples you get on a pond when you throw a stone. And as you know, these ripples are waves, the waves, as you know perfectly, surface waves. Okay, the speed of propagation of these waves is given by c, which is the square root of g times y. This speed of the surface waves will play an important role in the equations coming later. So the Froud number, we use this number, FR, Froud number, which is the velocity of the flow, V, over the speed of the waves, which is the square, as we said before, the square root of G times Y. So we have different, we are comparing the velocity of the flow with the velocity of the sound in the water. So depending on whether the flow is slower. If the flow is slower than the speed of sound, then we have Froud less than 1. If the Froud has exactly the same, then we call it this flow, we call it subcritical, tranquil, or streaming. If the velocity of the flow is exactly the same as the speed of sound, then the flow is critical, Froud number is 1. And if the speed of the velocity of the flow is greater than the speed of sound, then we have the Froud number greater than 1, and the flow is supercritical, rapid, or shooting. We won't go into too much detail on this. It's important to compare the pipe flow and with open channel flow. You already know, or you will see maybe next year, pipe flow. The pipe flow, the liquid is completely fills the pipe and flows under pressure. Okay, the flow in a pipe takes place due to difference of pressure gradient, and the flow in a closed conduit is not necessarily a pipe flow. Okay, you can have, as we saw before, a sewer. The sewer is a pipe, a closed pipe, and but it has a free surface. So and it flows by gravity, not by pressure gradient. Okay, so open channel flow, the flow takes place due to the slope of the channel bed due to gravity, so no pressure gradient, and the flow must be classified as open channel if the flow has a free surface, as we said before. Okay, we are going to derive the energy equation. We will use the following assumptions. First, we will assume steady flow, incompressible flow, uniform velocity at a given section, gradually varying depth so that the pressure distribution is hydrostatic, small bed slope, and no shaft work, no work due to fluid shearing at the boundaries, and no other work. So we can take a look here at the velocity profile. We said we were going to assume a uniform velocity profile and a pressure distribution, hydrostatic pressure distribution. So this is the energy equation we get from the previous assumptions. We can see that this is similar to the Bernoulli's equation, except instead of pressure, we have a new variable, which is two new variables, which are the flow depth y and the channel bed elevation. So both variables are somehow new in this equation. And of course, we have to add on the second side of the equation, we have to add the losses, HL. If we add more assumptions like constant slope, cross-section and depth, then the energy equation is simplified very much into the following equation. V equals 1 over N times the RH to 2/3 and SB to 1/1.5. So N is the Manning's roughness coefficient. We will see a table later. RH, you know, is the hydraulic radius, and SB is the slope of the bed in meters per meter. And it's important that this equation is only valid in SI units. Okay, this is a table of the Manning's number, Manning's N coefficient. We can see different linings, means whatever covers the channel bed. Okay, you can have concrete, asphalt, you can have rock, you can have fiberglass, whatever. Okay, and then depending on the depth ranges, you can get different Manning's numbers. They are obtained experimentally. We are going to look now at different the features of open channel flow. First, if you see a bump, there's a bump at the bottom of the bed of the channel. We have a bump, like a channel bump. So what we have here is the flow, the free surface contracts, and somehow the section is squeezed and gets thinner when it gets to the bump. That's a phenomenon of these channels when they come across a bump. Another feature of open channels is what we call hydraulic jump, and this is when the flow is going fast. The flow is coming from the left and is flowing very fast, high velocities. When it discharges into a zone of lower velocity, then a rather abrupt rise occurs. So this is what you see. Like it's there are no walls here. Remember, the open channels have no walls, top walls. There's a free surface indicated by that triangle floating on the. So it's funny to see the flow, the liquid surface rising abruptly when it gets to a slower region of the flow. Of course, you can have flow with gradually varying depth. That's something. Uh, so different depth, different slope, or same slope. And you can also have this is a discharge. You can measure the flow using the Weirs. Weirs is this plate, black plate we have at the end of the channel below the crest. So that plate, black plate, we have vertical plate is what we call Weirs, Weir, azud in Spanish. And then we leave you here an example for you to work with the previous equation, energy equation, and hope you do it right. Thank you.